me pull up the answer key for the gas laws chapter. My screen's being flaky. All right. So I think I got everybody who submitted graded by sometime this afternoon. And I did put some comments on errors and that sort of thing. I am going to go through this so we can talk a little bit about it. The first three here are predominantly geared toward getting you used to converting between the different pressure units. Millimeters mercury, atmospheres, and pascals are the ones that you see the most of. Torr, remember, is another term that also means millimeters of mercury. They are used interchangeably. They are the same unit, different words for the same unit. So the first one, you need to set it up so that your 1 atmosphere is on the top and your 760 are on the bottom. When you punch it into your calculator, you are essentially dividing by 760, and that should give you just over 4 atmospheres. Going back in the other direction, if you start with 3.5 atmospheres, you are converting to torr. It is still the same 760, only this time it is on the top of your fraction. So you are multiplying by 760, and this should give you 2,660 torr. Pascals, keep in mind, are a much smaller unit, and there are 101,325 of them in 1 atmosphere. So I'm going to divide, I'm going to take the number given, 328,243, and I am essentially dividing my 101,000s, and that gives you 3.23 atmospheres. Then we begin to head in the direction of all the different laws, famous dead guy laws. The first one actually makes use of Boyle's law. If you have pressures and volumes, and we are assuming that we are not changing the temperature while we're doing this, your equation has P1V1 equals P2V2. Once I sub all my pieces in, I then multiplied my 905 times my 3.1. That's where my 2805 and a half came from. Rearrange so that I am dividing by my 1230, and your final volume should be 2.28 liters. You can even kind of predict, looking at my two different pressures. I went from 905 up to 1230. Well, we know this is an inverse relationship. When one goes up, the other goes down. So even before I number crunched it, I was already expecting something less than 3.1 as my volume. For the next one, this one is Charles' law. It involves volumes and temperatures. We are assuming that the pressure is not changing while we're doing this. One hiccup I saw for a few people, you must convert your Celsius values over to Kelvin. Otherwise, you will not end up with the right ratios. So 7.5 over 308, and V2, that's your unknown one, over 253. I cross multiplied in order to do the math for this. That gave me 1897 and a half and 308 V2. One more division, I divided by my 308, so I get 6.16 liters. Gay-Lussac's law. Pressures end temperatures. Again, like pretty much everything in the gas laws, you need to convert to Kelvin before you put it into your equation. That way I end up with 2.1 over 948 and P2 over 373. This is another one where I cross multiplied in order to get rid of my denominators to give me 783.3 and 948 P2. Do your final division, 783.3 divided by 948, and you get 0.826 atmospheres. It stays in whatever unit you started with for that equation. However, when we get to the next one, because this one uses the ideal gas law, you have to use particular units. I gave you pascals, but the equation needs atmospheres. So I did my conversion. I divided my 110, 388 by my Pascal conversion value. And that gives me a little over 1 atmosphere, 1.089. I also need to do my Kelvin conversion. 55 Celsius, add your 273, that gives you 328. Now I can actually go back and start putting things into my equation. PV equals nRT. Pressure, it was in atmospheres now, 3 liters. N is what you're looking for. Your 0.0821 corresponds with the fact that you are using atmospheres and liters and Kelvin. And my 55 Celsius became 328 Kelvin. Multiply all the things that are numerical. That leaves you with a single unknown, my unknown being N. Your number of moles is 0.12. I know it's hydrogen sulfide gas. Sulfur is 32, hydrogens are each about 1. This gives me a molar mass of 34. So my final gram weight is a little bit over 4 grams. 4.09 because I rounded down a little bit. If you dragged a little bit, an extra decimal place with you, you might have ended up with like 4.11, I think, is what you get if you don't round quite so much. Switching to the combined gas law for number 8. P1V1 over T1 equals P2V2 over T2. So again, I'm kind of stuck with the idea of I need to do a little bit of converting here before I put everything in. I changed my temperatures from 37 and 68 up to 310 and 341. I moved the decimal place on my volume that was known and made it 0.75 liters. Plugged everything in, cross multiplied. That gave me the 1023 and the 1860 V2. One last division, 1023 divided by 1860 gives you 0.55 liters. If you left it in milliliters, that was okay. It wasn't really what I was expecting, but I didn't actually tell you which unit to put your volume in. Number 9 is stoichiometry. You have 10 grams of your reactant. Ammonium nitrate has a molar mass of 80 because it's got a nitrogen, 4 hydrogens, another nitrogen, and 3 oxygens. Once I divide that, I get 0.124 moles. The middle step, remember, for stoichiometry is going back to look at your balanced equation. I get 4 waters made from every 2 ammonium nitrates. basically you're multiplying by 2, but it makes it look better, more straightforward, if you go ahead and use the digits that are in the balanced reaction. So I stuck with the 4 and the 2. That gives you 0.248 moles. And because it asks you for liters, the liters conversion that we've been using all the way through this chapter is 1 mole at STP is 22.4 liters. So your final step is take the moles of the water vapor that you have and multiply by your 22.4, and you get just a little over 5.5 liters. And I don't have my square root sign here where it says molar mass equals, okay. And I probably should actually put that in maybe kind of like that.
Can I ask a question about number 9?
Yes.
So we weren't supposed to find the molar mass of the 2NH4NO3. It was just the NH4NO3.
Correct. Because the 2 is taken care of by the ratio step.
Oh, okay. All right. Thank you.
So this doesn't show it here. Remember that that when you're doing the density equation, this one is one that has a square root, and I realized that I didn't stick my square root symbol in front of it. dRT over P. This is another one that, just like the gas law, the ideal gas law, is really kind of specific to the units. Since I had grams and liters, I still need Kelvin for my temperatures, and I need atmospheres for my pressure. Using 715 gives you weird answers because it doesn't correspond with the fact that your 0.0821 is a unit that has atmospheres in it. It doesn't have millimeters mercury in it. Once you put everything underneath the square root and then do your division, and there's another, my square root didn't exactly go away until I got over here to that point there. Once you do your square root, then you have 61.78 as your molar mass. Keeping in mind that molar masses can't be less than 1, because even hydrogen weighs 1 by itself. On the other hand, molar masses for things that are in general chemistry, you're probably never going to see anything over 1,000. You'd have to have a huge molecule, like a hemoglobin molecule, in order to have a molar mass above 1,000. Then we get to Dalton's law. This one is the one that involves the partial pressures. The halothane is kind of a big messy molecule. You have to add it all together there. 1 carbon for 3 fluorines, another carbon, a hydrogen, a bromine, and a chlorine. That gives you 197 as your molar mass. So I have 0.076 moles.
Wait, I'm sorry. Say what law did you use for this one?
This is called Dalton's law.
This is Dalton's law. This one confused me.
This one pulls 2 pieces together. It pulls the idea of partial pressures together with mole fractions. So you have to do the mole fractions first before you can do the partial pressures thing. So I've got the left-hand one here is where my halothane is converted over to moles. For my oxygen, make sure you are dividing by 32 and not just 16, because it's a diatomic molecule. That gives you 0.706 moles. The 2 of them together have a total moles of 0.782. And then partial pressures, the mole fraction idea, says put each one on the top, divide by the total. That gives you 2 decimal numbers. And I left it in millimeters mercury, but if you converted it over to atmospheres, I also included the answers in atmospheres if you had converted it over to that. Your 83.6 and your 778 basically add up to the total pressure of 862. Most of it is oxygen, but a little of it is the halothane. This one I actually figured out how to do the root mean square velocity thing. I've got kind of sort of it where it's supposed to here. Square root symbol is 3RT over M. Some people forgot to put the M in kilograms per mole. You must move your decimal place in order for all the units to cancel out correctly. Everything on the top ends up being 7,058 and a half. The bottom ends up being 0.131. I divided, and then I finished off by taking my square root, and I got 231-ish. Keep in mind that one of the things that one of my tips was that in doing root mean square velocities, you are seldom going to see below 100, and you're also seldom going to see greater than 1,000. Root mean square velocities are almost always in the hundreds. Now, the last one is the rate of effusion one. And in terms of translating the information over into putting it in the equation, whichever gas is listed first is considered to be gas 1. Therefore, it goes on the bottom. Whichever one is listed second is considered to be gas 2. So the CO2 mass goes on the top. I did my square roots, and then I did my division. Most of the time, you will see answers reported as big one goes faster than, or little one goes faster than big one. So neon is smaller than CO2. And when I do the math for it, neon is 1.47 times faster than CO2. If you did it upside down, I gave you half credit, but it is upside down. You are supposed to do it in terms of how the information is presented. Questions for the homework set? Okay, let me shut my one file then. And we will go back to some more thermochem stuff. I don't know how far we're going to get. I don't think we're actually going to get to the end of the chapter today. However, being that this is Thursday, make sure you start working on your homework set over the weekend so that by the time we finish it up on Tuesday, you don't have all of it to do just in the span of a day or two. All right, I think this is where we stopped. We were talking about the bomb calorimetry versus the coffee cup calorimetry that we're going to be doing in lab. And one of the things that's mentioned in this part of the chapter is sometimes it's not grams when you're talking about heat capacities. You might see joules per mole Celsius or joules per mole Kelvin, and they refer to this as the molar heat capacity, as opposed to either just heat capacity by itself or specific heat capacity. Because remember, there's a little difference between those two. All right, new buzzword. Enthalpy is a delta H. The triangle out in front, remember, is an uppercase Greek delta, and it more or less stands for the word change. You will also see enthalpy referred to as heat content for a system under constant pressure. Remember, everything in this chapter is kind of, sort of about the system, because most of the time the surroundings are less important than the system. They're important, just less important. We're going to stick with our sign convention. Back on Tuesday, we talked about Q, and we said there's positive Q and there's negative Q. We're going to use the same signs again to also imply exothermic versus endothermic. So if your delta H is negative, that is supposed to indicate to you that the heat is leaving the system. Elvis has exited the building. For endothermic, your enthalpy is positive. The heat is being absorbed by the system. Now, one of these things, or this idea, implies that if you change states of matter, this also involves a heat change. If you're going from solid, liquid, or gas to a different state. So the first one ends up sounding kind of vaguely backwards. This is referred to as molar heat of fusion. And they put the little delta H in the spot there, and they write fusion down underneath. And this is not nuclear fusion, okay? This is something that is a solid melting to turn into a liquid, which sounds backwards because since it's the word fusion, you'd think that it should be a liquid turning into a solid. I didn't invent this. This is the way it's designed. Fusion is a one-way, it's sort of a one-way street there. So for instance, if you have an ice cube and you put it somewhere where it's maybe 1/10 of a degree above freezing, above 0 Celsius, if you let it sit there for a while, the temperature's not changing. You're still stuck at this like barely above freezing value. If you come back in a couple of hours, it's not an ice cube anymore, it's a puddle. Because at that constant temperature, you had melting occurring. Now, what if you are going back in the other direction? This one makes a little bit more intuitive sense. Solidification is going from the liquid to the solid. So those words actually kind of sort of go together. The two values are the same number. It's all about direction. So think about it this way. You have the ice cube. If you want your ice cube to melt, you have to put a little heat, at least, into the system. So note there, it says delta H of fusion, and there's no negative symbol there on the left-hand side, because it's endothermic. You have to put a little heat in to make the ice melt. But if you're going back in the other direction, if you have your freshly filled from the sink ice tray and you're sticking it in the freezer is removing heat as it's decreasing the temperature. So you have the opposite happening. Therefore, if you want something to solidify that was already a liquid, you got to have heat leave the system. And this is why it has a negative symbol. So let's talk about benzene for a minute. Benzene's a really cool molecule that we will cycle back to in a while. I was looking for my, I think my kids stole my, I was looking for my whiteboard. I was going to draw you a picture. Hang on a minute. I want to show you what a benzene molecule looks like. A benzene molecule has 6 carbons in it. And it's a really fascinating molecule because it's shaped like a hexagon. And it also has 6 hydrogens. And you end up with something that looks like this. Okay. See how we've got carbons that go all the way around the ring, and then these little doubled lines, and we'll come back to this later in another chapter. We're just sort of mentioning it at this point. These are called double bonds. And then each of my hydrogens is like a bicycle spoke, and they're all sticking out in opposite directions. At regular average room temperature, benzene is a liquid. Benzene is unfortunately a carcinogenic liquid. So definitely use with great care. Benzene freezes at 278.7. So basically not quite all the way down to 0 Celsius, because 0 Celsius would be 273 Kelvin. So kind of fridge temperature. If I want to melt it, if I have this little kind of icy block of benzene and I want to melt it, one, I need to know how much I have. I have 100 grams. I also need a conversion factor. So look at the math here. We've got 100 grams, and then I'm going to divide by the molar mass. 6 carbons and 6 hydrogens gives me a molar mass of 78. I have about 1.28 moles. Now the value, 9.87 kilojoules per mole, I looked up in the textbook. This is the fusion, the delta H of fusion for benzene. Note, moles on the top, moles on the bottom, those cancel out. My final answer is in kilojoules.
How did you get 9.87 again?
It's from the textbook. It's not a memory number. It's you either have to look it up or it is often given in the problem. If you look at examples in the back of this chapter, 1 or 2 of the examples, they actually give you the delta H values in the question. The other ones, I believe, say refer to table, and I can't remember actually what the table number is. There's a little table in about the middle of the chapter that gives you some average common substances and what their enthalpy values are.
So 78, it's atomic mass, right?
Yes, because it's 6 carbons and 6 hydrogens.
Okay, and 987, that's a constant.
Is the one I looked up in the textbook.
Okay.
For benzene, the delta H is 9.87 kilojoules per mole.
Is the benzene, is that the gas that we put in the car, right?
No. No.
Because
for air conditioning?
No, I mean for the vehicles. Like
no.
Gas for the vehicle, because I know in other countries they not call it gas, they call it benzene.
Oh no. Oh God. Benzene would No, just absolutely not, because benzene, when you burn benzene, that's like seriously bad news, because you get this smoky, evil, thick black smoke when you burn benzene because it has double bonds in it. Yeah, no, you would not want to put benzene in your car. Your car would lock up.
Yeah, it's surprised because, like I said, the whole Eastern Europe call the gas. I mean, from gas station, they call it benzene. I don't know why.
Yeah, because
Okay.
gasoline, okay,
Gasoline, yeah.
gasoline is octane, which is C8H18, with little trace amounts of pentane, isohexane, a little nonane, and in this country, a little ethanol. It's kind of a cocktail. It's not just one thing, but it's mostly octane. When you go to the pump and you stand there and you look at the, unleaded and plus and premium, and it has a number, that tells you what the percentage of octane is. Actually, let me draw you an octane molecule so you actually have some idea what this looks like. Octane also has carbons and hydrogens, but they are not in a ring. They are actually all kind of in one long flexible chain. It kind of looks like a bicycle chain in a way, because all of the hydrogens kind of stick out in opposite directions. So this is what an octane molecule looks like. Oct, because there's literally 8 carbons going across. Oops, I forgot to put 2 of my last hydrogens in there. They all have hydrogens. So this is your octane molecule, and this is what you want the most of. Okay, one of the reasons that premium gasoline costs more is because it's 93% this molecule, which means there's less gunk in it, which then also means it's harder to refine, harder to purify. Regular average unleaded, I think, is 87, which means only 87% of the molecules are this molecule, and the rest of it is stuff. Like I said, there's always ethanol in it in this country. The ethanol percentage varies depending upon the manufacturer and some other things like that. But yeah, no, I can't even think. I cannot even think of an internal combustion engine that would burn benzene and not be an almighty smoky mess. All right. Now we need 2 other phase changes. Liquid to gas, or back in the other direction. And I didn't have an easy way to put an arrow in here because, yeah, Microsoft Word doesn't like arrows really. If you are going from the liquid to the gas, so basically in the right-hand direction, if you're a biologist, you call it evaporation. If you are a chemist or a physicist, you call it vaporization. Which makes it sound like, you ray gun, zap, zap, you've been atomized. But anyway, because you are creating a vapor. However, all the sciences use the same word going back in the other direction. If you have gas and you're going back to a liquid, it's condensation. So just like the other 2 are paired, solidification and fusion are paired, vaporization and condensation are paired. Heat of vaporization, molar heat of vaporization, will come back again if you take the 112 class. We devote one entire lab to acquiring data to calculate the heat of vaporization for water, which is unfortunately kind of a boring lab. It's one of those where you do lots of waiting because you have to measure something and then you have to wait 6 to 8 minutes and measure it again. And then you wait for it to cool a little bit more and you measure it again. And eventually you get great data, but it's not a particularly exciting lab. If you dissolve something, you have delta H of solution, molar heat of solution. This is something that we will be doing in lab, or talking about more in lab. Ammonium chloride, remember that stuff that we baked off of our separation of a mixture sample about a month ago? We stuck it on the Bunsen burners underneath the hood, and that white smoky stuff went up the hood. Well, ammonium chloride is water soluble, because one of the questions that it asks you is, can you do the procedure? And it offers you some other options. And you have to sort of rationalize your way through it as to whether or not you could do it a different way. The delta H of solution for ammonium chloride is a positive value. When you put pure ammonium chloride in water, it gets colder. It's an endothermic reaction. And my value is positive 14.8 kilojoules per mole. So similarly to the benzene problem, I can do the same types of calculations here. And I can say, if I have 15 grams of ammonium chloride, 1 nitrogen, 4 hydrogens, 1 chlorine, has a molar mass of 53.5. So divide, I get 0.28 moles. Take my value that I just looked up, 14.8, multiply those two together, my moles will cancel out, and I'll get 4.15 kilojoules. So back to the lab thing for a moment. We did sublimation, okay? That was actually one of the terms that got mentioned in lab. You took something that was a solid, because when you weighed it out, all 3 or 4 grams of it that you weighed out, and then you heated it, it didn't melt. It went from a solid to a gas. Now, there is a term for going back in the other direction. If you have something that is a gas and it turns directly into a solid. All right, so things you could do that make this happen. If you have an old freezer, not one of the frost-free ones, and you get that iceberg that kind of builds up on the inside of your freezer and you have to thaw it out every now and again, that's deposition. All of the water vapor in the air is turning into ice crystals. There's no melting phase in between there. It's going from the gas to the solid. This is also one of the reasons why usually around here, it's not till January that this happens, but you go out in the morning and you have to scrape your windshield, all the icy gunk that gets to be on top of the windshield. That's also deposition. So mothballs and dry ice, that's sublimation. Scraping your windshield, that's a facet of deposition. There are things you can look up. There's 1 or 2 examples in your book. We're not going to do a whole lot in the way of calculations for that, other than just sort of mention in this chapter that it is a possibility. All right, we're going to do a little bit of Hess's law today. I won't get through all of this today. Remember we talked about sodium and sodium exploding and all that kind of thing? we're looking at the equation for it here. Sodium and water gives you sodium hydroxide, hydrogen gas, and heat, probably in the form of flame. This is a nice little exothermic reaction. So we can write heat as if it were an item. We can write heat on the right-hand side of the equation and almost pretend like it's one of the products of the reaction. It is a product, just not in kind of the more literal sense. If it was an endothermic reaction, you could write heat on the left-hand side. So look at the explanation or the version of Hess's law that they quote from the book. Basically, if you have parts, the parts add up to the whole. Okay, before we started class tonight, I ended up making muffins so my family can have them for breakfast tomorrow morning. And I took all the ingredients in the recipe and I put them all in the bowl and did all the appropriate things, and I end up with muffins. So all of the ingredients, all of the reactants, eventually total out to the products. We know that from the balancing reactions point of view. The same thing holds true if you are talking about thermochemistry. All right, so now I'm gonna kind of migrate my computer over because I need to be able to draw the board. It's almost there.
You keep forgetting that when you put it in here, you got to pull down the
Oh,
bit. Yeah, on the back. That way it'll fit better.
all right. So showing actually works better than just sort of looking at what's on the page there. So we're looking at a reaction that has iodine as a solid. Okay, that's part of that first overarching reaction. We add hydrogen gas to it. And the way this works, you get hydrogen iodide as a gas in the product. All right, so superficially, this actually looks like I have just one single reaction start to finish, two reactants, two product molecules. But the problem is, in reality, this is a two-step reaction. It actually takes 2 steps to get from the reactant side to the product side. The first step involves taking your iodine and sublimating it. So here we've got I2, but I've got an S underneath it because it's in solid phase. So I actually have to warm this up in order to get it to work. I have to get the solid to actually sublimate over into gas. Otherwise, the rest of the reaction doesn't work. But I also need some number values. And my delta H, my enthalpy, is going to be 62.44. And this is in kilojoules. All right, that's one of the 2 reactions that add up to this. My other reaction says take hydrogen gas, add iodine gas to it, and that gives me the HIs. Now, what makes that any different than the one on top? Note, this one is solid plus a gas. In this particular reaction, everything is in the gas phase. That's why it's a different reaction. It has number values for it too. My delta H is negative 9.44 kilojoules. Now, doing Hess's law problems is actually an awful lot like doing simultaneous equations in algebra. You want something to go away. So I'm gonna draw a line here and add my two reactions together, but I'm gonna get rid of the thing that is the same on the left and on the right. This is kind of like when you're doing algebra. If you have a 2x on one side and you have a 2x on the other side of the other equation, you can make them go away. So I'm going to get rid of my iodine gas here, because on this one, it's on the right-hand side of the reaction. And I'm also going to get rid of it on that one. So one on the right, one on the left. Total this downward so that I can make sure that what I have left over actually matches what I'm looking for. So iodine solid, hydrogen gas, HI is in the gas form, HI is in the gas form. And since I added my equations, I add my numbers. Positive 62.44 and negative 9.44 will give me a value of 53.0. So one of the things you will notice if you actually look through some of the examples that are in the textbook or some of the problems that are listed in the textbook is when they give you this problem, there's like 3 to 5 lines of information that they have to give you straight up. They look like very lengthy problems just in the presentation. Yet, if you look in the backs of the book, if this had been a homework problem that was in the back of the textbook, and you look for the answer, they're not going to show you all this. They're going to show you one thing. They're going to say the answer to this problem is 53. Okay. The idea is that by the time you get to the end of a Hess's law problem, all you have left is a number that matches the equation you are looking for. All right. There are rules for this. Some of the rules are pretty much the same ones that you see in algebra. And these are in your notes. If you reverse a reaction, okay, you're going to have to reverse the sign on your number value. Whatever your delta H is, that's going to be changed from a positive to a negative or from a negative to a positive if you flip-flop your equation, which you're allowed to. If you multiply by coefficients, you're also going to multiply action. So if your delta H was 300 and you multiplied everything through by 2, then your delta H becomes 600. Okay, sounds sort of more abstract in explanation than it does when you actually start sort of going through the process. So this one's actually designated as example 2 in your notes. Let me go through the steps and kind of show you how this works. We are looking for, so first they have to tell you which reaction you're trying to get to. So we want a delta H for C2H6 and hydrogen make 2 CH4. So that's the first line of the equation. Now I have 2 more lines. These are also given information. It's whatever you're going to need, they have to provide you some data to get there. Carbon plus 2 hydrogens gives you CH4, and 2 carbons plus 3 hydrogens gives you C2H6. And they give you H values. Your delta H for this one is negative 74.9. The delta H for this one is negative 84.5. All right. Where do I start? Doesn't really matter which one you pick on. I'm going to pick on this one first. I want it to look like this, but I only have this right at the moment. I don't have enough CH4s to make it match the one I'm looking for. So I'm going to take everything and multiply by 2. This will then give me 2 carbons plus 4 hydrogens gives me 2 CH4s, and I have to multiply by my 74.9 by 2 also. So I get negative 149.8. What about this one? My C2H6 is on the wrong side. I need to reverse this one. I'm going to write it back in the other direction. I'm going to write C2H6 becomes 2 C's and 3 H2s. But since I flipped it, since I flip-flopped the sides that everything's on, I need to change the sign of my delta H. It becomes positive 84.5. All right. Now I need to make sure things cancel out the way I want them to. 2 C's on the left, 2 C's on the right. I don't want any lone carbons in my end, so they go away. I've got hydrogens here and I've got hydrogens there. They don't match. This side has 4, that one side has 3. This is just like algebra. If I had 4x and 3x, 3 of them go away. So all of those go away. All but 1 of my hydrogens goes away. Hopefully this gives me what I need left over. So I have a C2H6, nothing there, but I have 1 hydrogen left. So C2H6 and 1 hydrogen. That went away, that went away. I have 2 CH4s left. Does it match? So C2H6, C2H6, hydrogen gas, 2 CH4s, 2 CH4s. Yes, everything matches. Add your numbers. My numbers then should give me negative 65.3. This is an exothermic reaction because it has a negative sign. One of them I multiplied by 2. One of them I reversed. I canceled out pieces following all the standard rules of algebra. And then I added my delta H values. It actually really is an awful lot like doing simultaneous equations. You have to flip things around. You may have to multiply or divide. Dividing is allowed also. This gets us kind of a little ways through the Hess's law portion. There are actually some additional segments to the Hess's law part, but I want to give you kind of a little bit of absorption time here. So we're not going to go through the other couple of examples tonight. I want you to have a little bit of time to think about it because it's not a particularly easy concept. I'm fighting with my webcam. There. Find a little gadget that holds it all together. Of course, now you see the middle of me. Okay, that's not too bad. Somewhere I have glasses. All right, so questions about what we have done so far in terms of Hess's law. Like I said, it may take you a little while to kind of figure out what your questions are. This is why I only want to do part of this segment tonight, because it's a big concept and it usually takes a little bit of brain perking time in order to kind of get it all to figure out how it matches.
Yeah, I think I'm going to look at the homework and see if that will bring any questions and see if I
Okay.
understand.
And there are some additional examples in the textbook. My examples are different than the textbook examples because I stole them from another textbook. So your textbook and the book that I stole them from aren't the same. Look at the examples in the book, look at the examples in the notes, hopefully giving you the weekend to kind of think about this. Write down answers. You can even send me questions for email going, how did you get from blank to blank? And I can try to provide you an additional explanation for that.
Okay, cool.
So other questions about either things like enthalpy and molar heat of fusion / solidification, or what we've covered part of Hess's law so far? Or are there questions about lab? Lab is a never-ending problem right at the moment.
I have a question about the test for this chapter.
Okay.
Is it so this test is 3 chapters combined, or is it it was just the
No, the last test of the semester will have 2.5 chapters. This one is gas laws and thermochem. 2 kind of different topics.
Oh, okay. So the chapter 6 is for the last test.
Yeah, 6, 7, and 2 sections of chapter 8 are on the 4th test.
Okay.
Yeah, I usually try to schedule it so that it's 2 to 2.5 chapters per test, because that way it sort of hopefully gives you a somewhat manageable amount of information. However, there is the final exam that does occur during exam week. That probably Tuesday of exam week will just be review and questions, because I'll probably do the 4th test the weekend prior to exam week. And that way it'll give me a chance to finish grading most of it. And also then for you to sort of formulate some questions. And I can give you a list of topics for the final exam.
Okay.
Yeah, we're halfway. Just in case it's relevant to anybody, the W date is approaching. I believe it is the 26th or 27th of October. So about a week or so from now, that's the 60% mark. So we are right about halfway in terms of number of weeks. We're actually more like 60 to 65% in terms of what we have covered, because the last week is mostly just review and testing.
Do we
Uh,
have a practical anything for lab?
No,
Or-
no.
No.
Even under normal circumstances, we don't do lab practicals. We tried that actually back when I taught for the beach campus. We had a couple of years in a row where we tried to construct this lab practical, but the problem was that even though we all do the same labs, we were trying to use a test that we all created jointly, which was really odd because not all of us tend to word the questions the same way. So that made it really complicated in terms of trying to explain to different sections of students. Oh, well, like, okay, these questions were made by Dr. Jane and these questions were made by Mr. Winters. And yeah, that didn't work very well. So I don't know if the beach campus ever returned to that after I stopped teaching at that campus. We discussed it a couple of times on the Norfolk campus and never found a really good method for doing it. So we don't.
Mhm.
a quick question about the last lab,
Mhm.
which was in person. Calculation by number 5, average percent of water in.
So you did it twice. You did 2 crucibles and you cooked them and cooked them and cooked them.
Mhm.
And then you did the math to figure out what the 2 different percentages were, which hopefully were kind of close. So it's just add the 2 of them together and divide by 2. You're just splitting the
I think
difference. So like if it was 48 and 50 were your percentages, your average would be 49 because 48 plus 50 divided by 2 gives you 49.
Okay. And the next page, you said the answer laboratory questions only 2 and 6, right?
Yes.
And next page, do we have to do anything with that?
Yes, that's the calculation of the formula of a hydrate. Take the mass of your anhydrous salt, divide by the molar mass, figure out how many moles. Take the mass of your water, divide by 18, because everybody's water is the same. How many moles of water? And then do moles of water on the top and moles of salt on the bottom, and round that to a whole number. Nobody should be getting numbers above 10.
Moles, you mean take atomic mass, right?
Yes, you need your numbers from the periodic table.
Okay, but you take like 1 molecule, right?
Yes.
Okay.
And there's an example in your notes about how to do those calculations. And there's an example on Canvas for the website for the lab section about how to do that also.
Okay, cool.
So there's 2 different examples you can look at to kind of figure that out.
It's a number chapter 4, right? Or no?
I actually think it was the end of chapter 3. I think it was the very last thing we did in chapter 3.
All right, I'll look it up.
But I know that it's in one of the note files.
Okay.
And like I said, and it's also on the lab page for Canvas.
Okay, thank you.
Okay, other questions about lab stuff? And I put this out as a reminder to everybody. I was like doing announcements today. Keep in mind that we have 1 month left of actual physical labs. So basically two lab cycles worth. After the Monday of Thanksgiving week, then I will not see you physically again. So you need to get as much paperwork to me as possible by Monday, November 23rd. Otherwise, you're going to have to scan it and submit it to me digitally. So I know that lab is complicated with this weird rotation schedule, but try to keep an eye on the grade listings to remind yourself of what you have not turned in yet. A lot of people have holes in their grades, as I'm sort of trying to catch up on all my grading. So take a look at that. Otherwise, I will see you on Tuesday.
Okay. See you Tuesday.
Bye.